Hi, everybody. This is going to be a presentation about forces of attraction that we're going to talk about with particles. And to get us started, I want us to consider this question here. What is the difference between intramural and interscholastic sports? I know that might seem like a strange question when we're going to talk about particles, but it'll really help us to understand the difference between intra and inter. So just take a second to think about that. Now, when you were thinking about it, were you thinking about intramural forces of attraction, or excuse me, intramural sports are sports that take place within the school, like, you know, let's say like the Frisbee tournament, maybe like the dance contest in gym, maybe a badminton tournament. Maybe there are, different for like a charity event, different basketball teams that form and they play against each other. They are within the walls of the school, and so they are intramural. Whereas interscholastic sports are sports that take place between different schools, like when Dallastown plays Red Lion in football, or when Dallastown plays Central York in basketball, between different schools. Okay. Now, what I want you to remember there is I want you to remember these different prefixes. That intra kind of refers to within. Okay. And if we're talking about intra-particle or intramolecular forces, we're talking about forces of attraction within the molecule. Like if we have an oxygen connected to two hydrogens to make a water molecule, okay, the intramolecular forces are these right here, the ones that are within the molecule. But then the intermolecular forces of attraction right here, that would be if you have another water molecule, and that's a little random line. You're going to see in these presentations, I get those sometimes. You remember how water is polar. Water is a polar molecule, meaning that, one end of the molecule, we have positive charges and the other end negative because of the electronegativity difference. The electrons move towards the oxygen, making this end of the molecule negative and the hydrogen end positive. Well, this negative end and the neighboring molecule's positive end, they might attract, and that right there between neighboring molecules, that is what is known then as an intermolecular or interparticle force of attraction. So an intramolecular or intraparticle force is within the particle or molecule, whereas an intermolecular force is between neighboring molecules. They might be the same molecule, or they could be, two different molecules. Like, water is, as we just discussed, polar, with this end being negative and this end over here being positive. Water can be attracted to maybe, like, for example, ammonia, which ammonia is also polar. And in the ammonia molecule, each of the H's have a positive charge, and the nitrogen carries a negative charge, and it's not symmetrical because three of them are bonds, and this one up here on top is a pair of electrons. But you can have like water attracted to water, or you can have water attracted to something else like, ammonia. That's an intermolecular force of attraction as well. Okay. So what you're going to be able to do by the end of this lesson is, of course, what's the difference between inter, which is between, and intra, which is within. There are some different intermolecular forces of attraction that we're going to introduce you to in this presentation. Okay, we're also going to, by the end, hope that we can look at the different substances and tell what type of intermolecular force of attraction they have. And then we'll define miscible and immiscible at the end, and kind of hopefully be able to tell which different types of substances mix with one another and which don't. It should be noted that the intramolecular forces of attraction, this is pretty much what you've been studying previously in this course, like the bonds, those covalent bonds within the molecule that's holding the molecule itself together, okay? This unit, we're going to be looking at intermolecular, between neighboring particles, and how does that affect properties? How does that affect whether something is a solid, a liquid, or a gas? But today we just want to know what the different forces are, and then be able to maybe identify them in different substances. That's a little tricky, and we'll have to practice that for a while before we get really good at it. So here's the different interparticle forces listed in general from the weakest to the strongest. First, we're going to look at dispersion forces, and we're going to look at dipole-dipole forces. Then we're going to look at hydrogen bonding, and then we're going to look at ion dipole attraction. You remember that the word dipole just means polar molecule. Like if we go back here and we look at, it's got to go way back, and we look at the water molecule, it is a dipole. It has a positive end and a negative end. Same with the ammonia. This end is really positive, this end's negative. So when you have something that is a dipole, that means it has two poles, a positive and a negative end to the molecule. It's a polar molecule. All right, we're going to start by looking at dispersion forces. And I know this might seem a little bit weird, but dispersion forces are present in things that are non-polar. Dispersion forces, in fact, they're present in everything, but they're the only predominant force of intermolecular or interparticle attraction in non-polar substances. These are a bunch of different hydrocarbons, and this is their boiling point data. They are all non-polar. Here, I'll draw the methane, for example. It is symmetrical. All of these are symmetrical with like a chain of carbons in the middle surrounded by hydrogens. So these are all, okay, they're all non-polar. So they do not have poles. They do not have positive or negative ends to the molecules. But this is generally an activity that we do in class, and we look at this and we say, all right, how is this list of hydrocarbons arranged? So I'll give you a second. Do you see how it's arranged? Do you see that it's just arranged alphabetically? Okay. Now we're comparing apples to apples here, like similar types of compounds. Okay. They're all made of just carbon and hydrogen. There's no other elements. And when they're arranged alphabetically, that's great, but it doesn't really let you see any kind of pattern that might exist with, the boiling points. So what I did was I rearranged it based on, to see this goes from lowest to highest boiling point. You see anything else now that falls into a pattern? Of course, it's no longer alphabetical, but is there something else that falls into a pattern? You see that the number of carbons is going up by 1, and that the number of hydrogens is going up by 2. See, we can see here, and I see a typo. The heptane should be a 16 right there. But we can see that as the molecule is getting larger, the boiling point is getting higher. Now, think about that. What does that tell you about the strength of the intermolecular attractions if it's requiring more energy to take the liquid and turn it into a gas where the particles are farther apart? Think about that. Yes, the larger the boiling point gets, that means that there are stronger intermolecular attractions. So the bigger the molecule is getting, the stronger the intermolecular attractions are. Okay. Now we said these are all nonpolar though. They don't have like a positive on one side and a negative on the other to attract. So what's causing this attraction? And of course, that's something scientists had to ask themselves. Hey, this molecule obviously has a lot of attraction because it takes a really high temperature to pull the liquid particles away from each other and get them to turn into a gas, but it's not polar, so what must be causing it? And that's where we get something called dispersion forces. They are temporary attractive forces between nonpolar molecules. Why are they temporary? Because they're caused by temporary or instantaneous dipoles. Like all of those molecules are made of, electrons that are constantly in motion. At any given moment, they could have within the structure of the molecule a temporary asymmetrical electron distribution. They don't stay that way because they're constantly in motion, but they could temporarily be distributed in an asymmetrical manner, which creates a temporary dipole. Because these dipoles are temporary and fleeting, it's not a super strong attractive force. That's why it's the weakest of the interparticle forces. If you go back to that first slide that had the 4 different types of interparticle forces listed, it is the weakest of all of them. But the bigger the molecule gets, the more electrons you have. So it's, easier to get a bigger polarization. And so with larger molecules, we do tend to see stronger dispersion forces. Now, because these forces of attraction are relatively weak, you really don't, they don't really have an impact over a great distance. Like I would liken this to, I'm holding a refrigerator magnet up and it's 1 centimeter from the refrigerator. I'm going to be able to let go of that magnet and it'll probably stick to the refrigerator. But if I hold it 10 feet from the refrigerator and let go, that magnet is not going to fly in and attach itself to the refrigerator door. And that's because the distance has weakened the strength of the force between them. Like they're not strong enough. I guess I shouldn't say the strength of the force is still there. It's just too much distance between them for it to bring them together. So these dispersion forces are relatively weak and they have a bigger impact when the particles are closer to one another. So that's why gases, mostly made of nonpolar molecules like carbon dioxide, okay, nitrogen, N2, they're symmetrical. CO2 is symmetrical because it's C double bond O, double bond O. And the symmetry makes it nonpolar. So, when they are gases, they're really far apart from one another. They don't really, the force of attraction is so weak, they don't have any effect on one another. But if you push them into a smaller volume and push carbon dioxide molecules closer to other carbon dioxide molecules, they will eventually solidify. And that's what we know of as dry ice. And why do they solidify? Well, when they're closer, their intermolecular attractions can finally make them stick, together. Now, all particles have dispersion forces, but typically, if the molecule is polar or ionic, it's going to have stronger forces that actually are the ones, that are predominant. The dispersion forces are weaker. That'd be like me, if I try to hang something on the wall with tape and it keeps falling down and then I eventually nail it to the wall, but I didn't bother to keep take the tape off. Is the tape maybe helping to hold it onto the wall? Are they attracted? Sure. That's not the predominant force. It's the nail that I put in that's holding it up. So that's dispersion forces. Now, dipole-dipole attraction, this is a little stronger in general than dispersion forces because it's a permanent dipole. The molecule is not symmetrical. And, we talked about like water, but you could even have something like, HCl, okay? And it's not symmetrical. The electrons, there's a difference in electronegativity. They're drawn to the element with the higher electronegativity. So this end of the molecule, wrong one. Let me erase anyway. You know, when you do like that little delta, that's partial negative, and this end is partially positive. So it's not ionic, but the electrons are all shifted towards the chloride. So this end of the molecule is negative and this end is positive. So if that's next to another polar molecule, and it could be the same molecule or a different one, but if it's next to anything that's polar, then, that's where, hey, in between here, these attract, and that right there in between the two polar molecules is called the dipole-dipole attraction. It's where your two dipoles are attracting to one another. Of course, how strong it is depends on the difference in electronegativity. The bigger the difference is, the more polar the bond is, and then that would make, the attraction in here stronger as well. And you can see, of course, that oppositely charged ends of the neighboring molecules are what are attracted to one another. So what's hydrogen bonding? Well, hydrogen bonding is when you have a dipole-dipole attraction, but it's hydrogen attached to one of these three elements. These three elements have the biggest electronegativity values, and they also have electrons that are by themselves, okay? For example, if I have HF, we've got these electrons that are by themselves. The electronegativity difference is so big that the shared electrons are being drawn towards fluorine. And what happens is that hydrogen is left like an exposed proton. Hydrogen only has one electron. It shared it with fluorine. Fluorine pulled it away. This end of the molecule is positive. This end is negative. I know this looks just like the HCl from the last slide, but the case here is that it is more extreme. There's a bigger difference in electronegativity. The neighboring molecule, same thing, partially negative, partially positive. And what it is just like a super strong dipole-dipole attraction between those neighboring molecules. That's super strong. Dipole-dipole attraction is given its own name. It's called a hydrogen bond. Okay. Water, because it's made of H attached to oxygen, hydrogen bonds to the neighboring water molecules, and that causes the boiling point to be higher than it would, typically be. If you look at boiling point trends for other things that are in the oxygen column, like H2S, H2SE, H2TE, they're all lower, and the H2O is way higher than expected. It's the attraction between the neighboring water molecules that makes the boiling point of water higher. Actually, if water followed the trend of the other elements in that family, water would boil at like negative 70 or 80 degrees Celsius, and we would not have liquid water on Earth. It would all already be vaporized because Earth's temperature is above that. You know how ice is less dense than water? When you think about it, ice cubes float in water. That's unusual. Usually solids are more dense than their own liquid because the particles are packed close together. But in water, okay, because the O from the one molecule has to be near the H from the neighboring molecule. Ice, the water molecules can't really pack in that efficiently. They let a bunch of open space. They actually get in these big hexagons, and there's a bunch of open space in the center that lowers the density. And, so the result is that ice is less dense than water. I can't think of anything else that is a solid that's less dense than its own liquid, just water. And then in biological systems, you guys remember the double helix from DNA and biology. I forget all the numbers from that, but what it's like G sticks. What is it? C and G and T and A, and the only certain ones can be across from each other on the two sides of the double helix. Well, what holds the two sides of the double helix together is a hydrogen bond, okay? So without hydrogen bonding, I mean, all the water on Earth would be in the gas form. The icebergs would sink and our water levels would rise. Ice would sink in ponds in the winter and fish couldn't live, under the surface of the ice like they do now. The DNA molecule, the two sides would not stick together. It's hydrogen bonding that is responsible, for all of that. So we can all just be very glad for hydrogen bonding. Now, the strongest type of intermolecular attraction is that between an ion and a dipole, because an ion has a full positive or a negative charge. It's not a partial charge, it's a full charge. Sometimes, like you might have an ion, for example, like calcium, has a +2 charge. So it's not just a full charge, it could be a full +2 or a full +3. You have negative ions that have full charges, -1, -2, -3. And these ions are going to be attracted to the polar molecule ends. For example, like, if I have a molecule of water, and remember we said this end is negative and then the hydrogen end is positive, the calcium is going to be attracted to the negative ends of the water. And let's say our compound had been calcium chloride. Well, the little and this is supposed to be an H, the chlorides, they're going to be attracted to the H end, right? They're going to be attracted to one another. So, that is ion dipole attraction. The ion is attracted to the oppositely charged end of the polar molecule. How strong it is depends on, are the particles packed close together? Then, of course, it's a lot stronger. The charge on the ion, the bigger the ion charge, the stronger that can be. And the magnitude of the dipole, like the more polar the molecule is, the stronger the attraction is going to be to ionic things. So this is a little practice. Look at all of these and see if you can figure out, and number 6, I don't know if you can see that, says Ne. Take a few minutes and just kind of go down through there and see if you can figure out, like, what kind of interparticle attraction would exist, between, like, the molecules of the following substance. Like, for example, HBr, is that symmetrical or not? It's not symmetrical. Okay. You got to look, electronegativity difference, and then neighboring molecule, there can be interparticle attractions. Okay. So you got to look that up and, decide. Okay. So you got to decide what kind of molecule it is, and then, decide what kind of interparticle attraction you might have. So, did you look those up? So the bromine, oh gosh, sometimes I hate, hasn't done that to me too much today, but you'll see on some of these, it does it to me a lot. Okay, so the bromine has an electronegativity of 2.8 and hydrogen's is 2.1. Those are on our periodic table. So the electron's going to shift towards the bromine, make it negative, hydrogen's positive. So this is a dipole attraction because they're two polar molecules attracting to each other. Hydrogen end's positive, the bromine's negative, so the poles are attracting. All right, so see if you can do the other ones. Think about what they are. You know water is polar, right? Do you recognize this as ionic? How do you know it's ionic? It's made of metal and nonmetals. Magnesium's +2, sulfate's -2. So what's holding this hydrate together is the ion is attracted to the dipole. How about CO2? You see that it's symmetrical, so it is non-polar. What's the only kind of attraction that can be present in non-polar molecules? Dispersion forces. Okay, look at the next few. Okay, the HF is just like the HBr, and perhaps you remember me using this as an example. Here we have hydrogen attached to a fluorine. Okay, they have to be attached to each other for it to be hydrogen bonding. It would hydrogen bond to the neighboring molecule. Okay, but remember, they have to be attached to each other for it to be hydrogen bonding. If you had, for example, if you had a formula like this, CH3F, where the C is attached to an F and 3 H's, that is not going to be hydrogen bonding. And you know why? Because the fluorine is not attached directly to the hydrogen. For it to be hydrogen bonding, you have to have oxygen, fluorine, or nitrogen attached to the hydrogen itself. And so this one is going to be a hydrogen bond. How about this next one? Think about the structure. Those would all be H's. Just see right here where we have the H attached to the O. Hydrogen bond. And then how about neon? I mean, here it is. That's what it looks like, 8 valence electrons. It's symmetrical. If it's symmetrical, that means it is nonpolar. What's the only kind of intermolecular attraction present in nonpolars? Dispersion. Okay, so here's your answers. How do we know what can mix? If something is able to be mixed, it has to be attracted to one another. So like polar can mix with other polar because of the dipole-dipole attraction. Polar and ionic, like ion dipole attraction, they can often mix. Not all, when we'll get into this in Unit 10, not all ionic substances are soluble, though, in all polars. Sometimes the ions in their crystal lattice, they are sticking to each other with such a great force of attraction that they'd rather stick to each other than be attracted to the polar. So not all ionics will dissolve, in the polars, but most will. Many will, I should say. And then nonpolars will mix with nonpolars. There's nothing opposing them mixing. There's no like if I put water with oil, the water is attracted to itself and oil is nonpolar, so it's not attracted to it. They won't mix. That's immiscible when they are unable to be mixed. Polar will not mix with nonpolar. But if I have two nonpolars, there's really nothing opposing them intermingling. Especially if they're in the liquid or the gas phase, if they're able to move and there's nothing like keeping them attracted to something else, they'll just get into each other's space. They'll increase what's called the randomness. You'll learn a little bit about that in AP Chem. So polar and polar mix, nonpolar and nonpolar mix, Ionics can often be dissolved by something polar. Ionics are not going to be dissolved by something nonpolar. I mean, there's no attraction between ions and a nonpolar molecule, so they will not dissolve. So hopefully you know the difference now between inter and intra within the molecule and between neighboring molecules. From weakest to strongest, we have dispersion forces, which are nonpolar molecules. Dipole-dipole, which are two polar molecules. Hydrogen bonding, which is when you have polar molecules that have hydrogen attached directly to oxygen, nitrogen, or fluorine. And then the strongest of the intermolecular is when an ion, a full-fledged ion, is attracted to a dipole. Okay, we did that practice on the previous slide, and there'll be more practice coming up. And remember, the ones that are miscible, polar with polar or polar with ionic. The ones that are not miscible, that are immiscible, that would be, immiscible would be polar and nonpolar, or ionic and nonpolar, they can't mix. And then the last situation which can mix is nonpolar. In the liquid or the gas form, they'll just go ahead and mingle. So hopefully that helps. And, after you watch this, make sure you, read what's in the book and feel free to email me, with any questions. Okay. So good luck with everything. It's always fun getting back to stopping. There we go.